In this video, we are going to discuss numerical solutions to ordinary differential equations. Ordinary differential equations, or ODEs, are differential equations containing one or more functions of one independent variable and the derivatives of those functions. The idea in solving ODEs is to solve the equation as shown. The differential equation is used to estimate the slope in the form of the first derivative at x sub I. In other words, the slope at the beginning of the interval is taken as an approximation of the average slope over the whole interval. The simplest approach is performed using Euler's method. In this method, we first set f of x sub I, y sub I to phi, where the function f is the differential equation evaluated at x sub I and y sub I. The parameter phi is used as a slope and substituted into the equation y sub I plus 1 is equal to y sub I plus f of x sub I, y sub I times h in order to determine the next value of y. The technique is seen best with an example. Consider the ordinary differential equation shown. Let's first solve the ODE analytically. Using techniques we learned from calculus, we obtain the solution as shown. Y equals negative 1/2 x to the fourth plus 4x cubed minus 10x squared plus 8.5x plus 1. We now use Euler's method to find the solution to the differential equation. Here's how we do it. The first step is to assume f is equal to dy over dx, which is essentially the slope of the function y at the position x. Now x is evaluated from 0 to 4 with a step size of 0.5. The initial condition at x equals 0 is y equals 1. So, using this equation, y sub I plus 1 is equal to y sub I plus f of x sub I, y sub I h, we can now solve for the next value of y at the next value of x. At x equals 0, y is equal to 1. The next value of x is 0.5. So the question is, what is the value of y at 0.5? So using this equation, we want to get y at 0.5, which is then equal to y at x equals 0 plus f, since x equals 0, then we put 0 here, and since y equals 1 at x equals 0, then we put y here. And since we determined the h to have a step size of 0.5, then we put 0.5 here. Now f of 0, 1 is this equation. Since this equation contains only x, the variable x, then f of 0, 1 is equal to simply 8.5. That's what we have over here, 8.5. So this is 8.5 and this is 0.5, and x y at x equals 0 is equal to 1 according to the given. So this is 1. So we can now solve for y at 0.5 at x equals 0.5, and that is equal to 5.25. Now the true solution using this analytical equation is at x equals 0.5 is 3.21875, and thus we can get the relative percent error to be 63.1%. Now that we know what the value of y is at x equals 0.5, we can now get the value of y at x equals 1. Remember that we have a step size of 0.5, so the next value of x is 1. So we can get this value using this equation. So for the second step, we have y at x equals 1 equals y at x equals 0.5 plus. Now we can use x equals 0.5, and at x equals 0.5 we have y equals 5.25, and that's what we have here. Then of course we multiply that by h. So we evaluate this, we plug this in here, or we plug the values of x in here, and we get for f of 0.5, this should be 0.5, 5.25 to be equal to 1.25. So we multiply 1.25 by 0.5 and then add it to 5.25, and we get for y at x equals 1 the value of 5.875, which is what we have here. So we do that for 1.5. We use this equation to get 5.125 for x equals 1.5, and so on and so forth. We can also get the true values using this analytical solution, and we find that at least for the second step, there's a 95 or 96% error. Okay. When we complete the calculation, we immediately see that the error is quite large. You can see it here. So we begin with 63%, 96%, and then at x equals 1.5, we have 131%. At x equals 2, we have 125%, and so on and so forth. This is because of the basic assumption of the Euler's method, that is, the slope is determined by the value of the ODE at the initial position. So taking a look at this graph, the blue graph shows the analytical solution, while the red dots shows the numerical solution. Okay, so this value of y at x equals 0.5 was obtained because at this value of x, so at x equals 0, where y equals 1, the slope is determined by the line, or the tangent line at this point. Now, if we take a look at the tangent line, you see that the tangent line, or the slope of that tangent line, is valid only at this point. As we go up, the slope changes. And the reason for this very large error here, 63% error, because at this point, the slope is already smaller compared to the slope here. And that was what we meant that when we said earlier that the value of the slope is determined by the initial value of the function. So the error is caused by that by that assumption. Since we began with a large error at the first interval, and since our succeeding solutions depends on what we obtain in the first interval, then the errors will just pile on top of each other. If the function y is smoothly varying, then the error won't be so large. But this function is a fourth order polynomial, and it's not a smooth function, as you can see. Okay, and furthermore, the step size is quite large. A smaller step size would help in decreasing the error. So let's take a look at how this was implemented in MATLAB. So in order to generate this blue curve, I used these two equations. So this is the analytical solution, and this is the x values, so that I can have definite values of smaller intervals for x. Okay, so that I can draw a smoother function for the function y. If you don't know what linspace is a function that generates data sets between the first or the minimum value and the maximum value. If you don't put a third argument here, this means it's going to generate 100 numbers between 0 and 4. So I have about 100 data points in this curve. So x true is my x value for the blue curve, and y true are my y values for the blue curve, and it's the analytical solution. Okay, now let's solve for the solution to the differential equation using Euler's method. Now, Euler's method involves the determination of y sub I plus 1 from y sub I plus the function f of x sub I times h. Here I set the h to be equal to 0.5. The initial or the boundary condition of y is equal to 1. The minimum value of x is 0 and the maximum value is 4. That means that my interval, that means that I need to have 9 data points. So if this is 0 and this is 4, and and I have 0.5 between from 0.4, I have a 0.5 interval between 0 and 4, then that means there are 9 data points: 0, 0.5, 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means that I have 4 minus 0 divided by 0.5, that's 8, and then I add one more for the extra data point, so that's the number of intervals or the number of data points that I get for the value of x. Now I'm using that because I'm going to change the value of h later, just to show you that this becomes more accurate when when h becomes smaller and smaller. So now I define x to be equal to the lin space of the minimum value of x up to the maximum value of x with this number of data points. So in this case, since I have since my h is 0.5, I need about 9 data points in this interval. So this implementation is quite straightforward for the Euler's method. This f is my differential equation dy dx, which I defined here as a function. So f of x is equal to y equal to negative 2 times x cubed plus 12x cubed plus 20x plus 8.5. Okay, so that's pretty straightforward, and once I run this, okay, I get this graph. Okay, notice that if I decrease my h value from 0.5 to 0.25 and I run it, the difference between the blue curve and the red dots becomes smaller. If I change this again to 1.1, then you see that it's becoming smaller, or the error becomes smaller and smaller. And then if I make h equal to 0.1, you see that it's actually almost overlapping. So this is what I mean when I said earlier that you can reduce the errors by decreasing the step size. So the other sources of error are the truncation or discretization errors caused by the nature of the techniques employed to approximate the value of y. Round-off errors caused by the limited numbers of significant digits can be retained by computer is also a factor here, but it's not a big factor, and it's not even the biggest factor. Now, the Runge-Kutta method is the method of choice in solving ODEs. It succeeds virtually always. It's not usually the fastest method, and if computational efficiency is of no concern, then one should choose the Runge-Kutta methods. Runge-Kutta methods achieve the accuracy of a Taylor series approach without requiring the calculation of higher derivatives. Many variations exist, but all can be cast in the generalized form as shown, where phi is called the increment function, which can be interpreted as a representation of the slope over the interval. At first glance, it's just similar to the Euler equation in Euler's method. But if you look closely, you will see that the function phi is a function of the dataset x sub I and y sub I, as well as the step size h. So the increment function can be written in general form as this. Phi is equal to a1 k1 plus a2 k2 plus and so on and so forth up to a sub n k sub n, where a's are constants and the k's are given by this. So k1 is equal to f of x sub I y sub I, k2 is equal to f of x sub I plus p1h, y sub I plus q11 k1h, k3 is equal to f x sub I plus p2h, y sub I plus x21 k1h plus plus q22 k2h, and so on and so forth, where the p's and q's are constants. Notice that the k's are recurrence relationships. So various types of Runge-Kutta method can be devised by employing different number of terms in the increment function as specified by n. Once n is chosen, values for a's, p's, and q's are evaluated by setting the generalized form equal to terms in a Taylor series expansion. So that's what we're going to do in the next slide. We're going to begin with the second order Runge-Kutta method. So the second order version of the generalized form is y sub I plus 1 is equal to y sub I plus a1 k1 plus a2 k2 times h, where k1, as we've discussed before, is f of x sub I, y sub I, and k2 is equal to f of x sub I plus p1h, y sub I plus q11, k1h. Now, recall that the Taylor series for y sub I plus 1 in terms of y sub I is written as y sub I is equal to y sub I plus the function of x sub I, y sub I times the interval h plus first derivative of the function x sub I, y sub I times h squared over 2 factorial. So we ignore the higher order terms here, the terms involving h cubed. F prime of x sub I, y sub I must be determined by chain rule differentiation. So if we do a chain rule, f prime of x sub I, y sub I, it will be equal to partial of f with respect to x plus the partial of f with respect to y multiplied by the partial of y with respect to x. So we put all of these into this part and get this. Okay, so y sub I plus 1 is equal to y sub I plus f of x sub I, y sub I times h plus the partial of f with respect to x plus partial of f with respect to y, partial of y with respect to x times h squared over 2 factorial. I'd like for you to remember this or put it down or write it down on a piece of paper just for you to remember it. And then we're going to use it in the next slide. So we're now going to use a Taylor series to expand the expression for k2. And remember that k2 involves the function f, where the function f is dependent on x sub I, y sub I, and h. So what we need to do here is to use a dummy function g, where it has two variables x and y. So we're going to take a look at the Taylor series of these two variable functions. So g is equal to x plus r, y plus s, which is equal to g of xy plus r, partial of g with respect to x, plus s partial of g with respect to y, and so on and so forth. We use the same technique on k2, or specifically on f. Okay, so what we obtain is f of x sub I, y sub I plus, this is our r, so this will become p1h partial of f with respect to x. This is our s. Okay, so this becomes q11 k1h plus partial of f with respect to y plus the higher order terms in the Taylor series. Now that we know k2, we substitute k2 here and we substitute k1 here. Remember that k1 is just equal to f of xi, y sub I. Y sub I plus 1 is equal to y sub I. That's what we have here. a1 times h f of xi, y sub I plus a2 h times f of xi, y sub I, a2 p1 h squared, partial with respect to x of f, and then a2 times q11 k11 h squared, f of x sub I, y sub I, partial of f with respect to x. Now if we collect terms with the same order of h, so this is h to the first power, this is h to the first power, this is h to the second power, this term is h to the second power, we have y sub I plus 1 is equal to y sub I h multiplied by this term and h squared multiplied by this term. Now we compare this equation to the equation that I asked you to write a while ago. So it's this equation. We can see that if we compare this term here with this term here, you can see that a1 plus a2 is equal to 1. And if we compare this term here with this term here, we see that a2p1 is equal to 1/2. Also, we compare this term and this term here, we see that a2q11 is also equal to 1/2. So we obtain a1 plus a2 is equal to 1, and a2p1 is equal to 1/2, and a2q11 is equal to 1/2. We have 3 simultaneous equations and 4 unknowns. Thus, there's no unique set of constants that satisfy this equation. What we can do is assume a value for one of the constants so that we can determine the other 3. Okay, so consequently, there's a family of second-order methods rather than a single version. In other words, since we are assuming the value of one of the constants, we can have a family of all these equations depending on what the value of the chosen constant is. For example, if we specify a value for a of 2, then a1 is equal to a1 minus a sub 2, and p1 is equal to q11 is equal to 1 over 2 a sub 2. Okay, so we have a family of solutions for a11 and also a family of solutions for p1 and q11 depending on the value of a2. Every version would yield exactly the same results if the solution to the ODE were quadratic, linear, or constant. However, they yield different results when the solution is more complicated. So, let's say, for example, that A2 is assumed to be 1/2. Then A1 is equal to 1/2 and P1 is equal to Q11 and is equal to 1. So these parameters, when substituted into the generalized form, yields, so we remember y sub I plus 1 is equal to y sub I plus A1 K1 plus A2 K2H. And since A1 is equal to 1/2, then we have 1/2 here. A2 is equal to 1/2 as well, and K2 or P1 and Q11 is equal to 1. So we have 1/2 K1 plus 1/2 K2 here. K1 is equal to f of x sub I, and K2 is equal to f of x sub I plus h, y sub I plus K1 sub h. Okay, we already used P1. We already know that P11 and Q11 is equal to 1, so that's why we have x1 plus h here and ayi plus k1h here. Okay, so what do we do here? Well, we actually do the same, we actually go through the same process as what we did in Euler's method, but instead of just using this equation, we need to determine k1 and k2 first. K1 is just equal to f of xi y sub I. K2 is now equal to f of xi plus h y sub I plus k1h. If K2 wasn't present, so if this wasn't present and if A2 is equal to 1, then that would be Euler's equation. We would be doing Euler's method. Okay, so for this method where A2 is equal to 1/2, this is called the Hun method. Okay, so first we determine K1. Okay, use the function f. We determine K2 and use the function f and plug in x1 plus h and xi plus h and yi plus k1h. Okay, so we need k1 first in order to get k2. Plug the values of k1 and k2 here, multiply by h, and then add that to y sub I. We get the new value of y sub I plus 1. If A2 is assumed to be 1, then we have the midpoint method. A1 is equal to 0, P11 and Q11 is equal to 1/2. This means that y sub I plus 1 is simply equal to y sub I plus k2h. We don't need k1 here, but we need k1 to determine k2. So k2 is equal to f of x sub I plus 1/2 h times y sub I plus 1/2 k1h. Ralston's method assumes that A2 is equal to 2/3, which means that A1 is equal to 1/3 and P11 is equal to Q11 is equal to 3/4. These parameters, when substituted into the generalized form, yields this equation. Y sub I plus 1 is equal to y sub I plus 1/3 K1 plus 2/3 K2 times h, where K1 is given by this, and K2 is equal to f of x sub I plus 3/4 h, y sub I plus 3/4 K1h. The third order Runge-Kutta method is derived similarly to one of the second order method or to the second order method. Okay, but instead of just using 2 terms in the Taylor series, then we use 3 terms in the Taylor series. The advantage of using the third order Runge-Kutta method is that now you can do ordinary differential equations for cubic equations. Okay, so in this case, for this specific case, you have y sub I plus 1 is equal to y sub I plus 1 over 6 times k1 plus 4k2 plus k3 times h, where k1 is given by this f of xi y sub I, k2 is equal to f of xi plus 1 half h y sub I plus 1 half k1h, and k3 is given by f of xi plus h y sub I minus k1h plus 2k2h. So again, first you need to determine k1 using the function f. From here, you use k1 here to get k2, and to get k3, you use k2 here. Now that you know k1 and k2 and k3, you plug this in here, multiply all of these by h, and then you add that to y sub I to get y sub I plus 1. Okay, and then you iterate that over and over again, depending on the number of your data points. For the fourth order Runge-Kutta method, which is the most popular of the Runge-Kutta methods, there are also an infinite number of versions depending on the assumed value of the constants. So this form is the most commonly used equation, and we call it the classical fourth order Runge-Kutta method. So y sub I is equal to y sub I plus 1 is equal to y sub I plus 1 6 k1 plus 2k2 plus 2k3 plus k4 times h. And k1, k2, k3 are given by these equations. So again, you first determine k1, where k1 is just equal to your f of xi y sub I. You plug in k1 here to get k2, and then you plug in k2 here to get k3. You plug in k3 here to get k4. Once you know all the k's, you plug these here, perform this equation, multiply it by h, and then you add it to y sub I to get y sub I plus 1. So this is the method that you're going to use for your machine problem. The fifth order Runge-Kutta method or one of the solutions is given by this. This is Butcher's fifth order Runge-Kutta method. Okay, so you can go through that at your own pace or at your own time. Okay. Now let's consider an example, and we use the same equation as before. Differential equation as before. dy dx is equal to negative 2x cubed plus 12x squared minus 20x plus 8.5. We also use a step size of h equals 0.5 and an initial condition of y equals 1 at x equals 0. So the first data point is x1 equal to 0 and y1 is equal to 1. So first we determine k1. So k1 is equal to f of 0, 1. So we plug in 0 here, 0 here, 0 here, we get 8.5. So k1 is equal to 8.5. We put 8.5 here. We know that h equals 0.5. We know that y1 is equal to 1. Now h equals 0.5 and x1 is equal to 0. So that means that we're now solving for f of 0.5 divided by 2 and 1 plus 1 half times 8.5 times 0.5. All of that is in here. So now you can solve for this function, and that function will give you 4.21875. So now that after determining k2, you put k2 here, and you solve for k3. k3 is given by f of 0 plus 1 half 0.5, 1 plus 1 half times k2, which is 4.2 times 0.5. And from there, you determine k3 to be equal to 4.21875. Once you know k3, you determine k4, plug in k3 here. Okay, so you can get k4 by using this equation. Okay, x1 is 0, y1 is 1. So h is 0.5, k3 is 4.2, and h is 0.5. So k4 is just this function evaluated at these numbers, and that is equal to 1.25. So k1 is 8.5, k2 is 4.2, k3 is 4.2, and k4 is 1.25. Okay, you perform this operation, multiply this by 0.5, add it to 1, and then you get y1. It's equal to 3.21875. If you recall, the value of the function at x equals 0.5 is actually 3.21875. which means that we're actually exactly correct, and that the error is 0 at least to 5 decimal places. Okay, now what if you have an nth order differential equation? If you've noticed, we have discussed a solution for a first order ordinary differential equation. If you have what if you have an nth order differential equation? In such cases, you will need to break down an nth order differential equation to n number of first order differential equations. Let's take a look at this example, where we have a second order ODE. In this example, we need to break it down into two first order ODEs. Our first ODE is the most obvious and is just the differential with respect to time. So y is equal to dx dt. Once you substitute this equation to the original second order differential equation, you should be able to derive the second first order, the ODE. So, fortunately for you, almost all of the differential equations that describe the behavior of nature are up to second order only. Now, the next step is to solve for the two ODEs simultaneously, and what that means is this. Since you're using Runge-Kutta, and you're solving for the values of y at each step or at each value of x, you're also going to do that for each of these equations. How do we implement the Runge-Kutta method in this case? So notice that this equation has a dependent variable x and an independent variable t. So what if we start with t equals 0 and x corresponding to t equals 0. So let that be x1. So let's say we know t1 and x1, which are the initial or the boundary conditions. So we want to solve for x2. And if we have a step size of h, then we know that t2 is just t1 plus h. Okay, so what we are going to do here is to first use Runge-Kutta method here. Okay, we first need to solve for y, okay, using Runge-Kutta method. Once we solve for y, we plug whatever we get here, and then we solve for x to get x2 at t2. And that's what we mean when we say that we should solve the solution, or we should solve this differential equation simultaneously. So to get to the next step, x3, we first need to solve for y3 here using this differential equation, and then plug y3 there to get x3. Okay, then for t4, we solve y4 using this differential equation, and then plug in y4 here, and then use that to get x4. Okay, and so on and so forth. Now, the Runge-Kutta technique is a very powerful technique. It's important to know the basic technique in order to understand and appreciate more advanced methods in solving ODEs. In the last machine problem that you will do for this course, you will be able to get a chance to implement the fourth order Runge-Kutta technique to any differential equation. Good luck!